Okay, we're going to lecture here on the final chapter here of the season. So it is chemical kinetics. We're going to cover what's in this chapter, and I'll let you know, obviously, what from this chapter you'll be responsible for the final. Obviously, it won't be everything in here. So chemical kinetics, kinetics deals with really in chemistry the study of sort of how fast or slow a reaction is. And that's really the area where we deal with chemical kinetics. Something you'll learn if you're going on to 200B, which is thermodynamics. Thermodynamics kind of deals with whether or not sort of will a reaction take place a lot of times. So these two things are sort of related to each other. There is sort of a relationship between sort of kinetics and thermodynamics, but really that study of kinetics sort of deals with, like I said, sort of how fast or slow a reaction is going to kind of take place. So one way that we oftentimes sort of look at kinetics and sort of rates of reactions is reaction rates. And when we talk about a reaction rate, oftentimes we're looking at really the change in the concentration over time. So very commonly we'll see these sort of units, which is molarity over seconds. And a lot of times this is the rate of what we're looking at in a chemical reaction, which is sort of the change in concentration over time, which obviously is a rate, how fast you do something per period of time is some type of rate. And when we look at the reaction rate, it is that change in concentration over time of, you could do it for reactants. You could also do it in relationship to products. A lot of times, obviously, in these reactions, reactants sort of concentration over time should be decreasing, and our products over time in a reaction should be increasing. As we know, in a sort of a one-way sort of reaction, we have our reactants that go to products. So as time goes on, we need to obviously use up our reactants in order to make our products. So we do see over a period of time a decrease in the amount of reactants and an increase in the amount of products. This gives us an opportunity for both reactants and products to write what is sometimes referred to as the rate expression. And the rate expression is just that. It sort of expresses how the concentration of either a reactant or a product is changing with time. So if we were to look at this particular reaction here, A goes to B, for a reactant, we could say that the rate is equal to the change in the concentration of A. A reminder that when you do see this sort of brackets around something, those brackets basically mean concentration. And in most cases, the type of concentration that we're talking about is molarity, which again is our moles per liter. So again, that's typically what those sort of brackets refer to. So in the case of our reactant here, the rate is equal to minus delta, the concentration of A, or the change in the concentration age, and the delta means change, the concentration A over the change in time. Because it is a reactant, the reason for this is we would expect it to be decreasing with time, as I mentioned. So when we write these rate expressions, we do include a negative here in the rate expression for our reactants, because we should have sort of that lowering of the concentration as time goes on. When we get to our product side, which is our B, we have the rate is equal to the change in concentration of B over the change in time. In this case, there is no negative here, and that is because this is sort of a positive change that's going to happen. We are increasing the amount of products in this case over a period of time. The real reason as well is for the negative being there for our reactants and the kind of no negative being there for our products is, typically speaking, when you calculate this rate, these guys are usually positive numbers. And in order for it to be positive numbers, we do sort of need that negative there to get it to a positive value. So for example, if we were looking at this reaction of, say, A going to B in this particular case, if we just kind of look at just some made up sort of concentrations, if you will, of A going to B, initially we would have perhaps all of A and really none of B. And maybe at the end there, we'll have like 2 molar of A, and maybe we have like 3 molar of B, whatever it may be. So when we would look, for example, at the change in the concentration of A, change in the concentration of A would be really kind of the concentration of A at the final minus the concentration of A at the initial. And in this particular case, with my made up numbers here, you can see 2 minus 4 is going to give you a -2, say, molar. And that negative, along with the negative that we put here, will turn our rate into a positive number. So that's really the sort of math reason why we have that negative there, because it is decreasing with time. That will always get us sort of that positive rate that we need. We all don't need it here on the product side, because we could do the same thing. For example, here, the change in the concentration of B in my made up example would be 3 minus 0, which would give me 3 molar. This is a positive number, along with no negative there, keeps my rate positive when I do calculate it. So always when you are writing sort of these rate expressions, anything that is a reactant, because it should be decreasing with time, will have that negative incorporated into the rate expression to allow you to end up with a positive rate. Any questions on that there? And when we do look at a reaction, and sort of kinetics reaction, for example, here we can see with our circles at the start here, we pretty much have all of our A circles. And as we start with time here and start going through different time period here as the reaction is taking place, we start to see the disappearance of our reactant circles, and we now start to see the appearance here of our product circles representing B. And as time goes on, obviously, you can see a lot more of the product sort of circles happening in this reaction, which is what we would expect in this reaction, as it's a one-way reaction. Everything's going to dump out on the product side. So we should get those conversion of reactants into products. Again, graphically, which in kinetics deals with a lot of graphs. So when you do a lot of kinetics problems, the one thing that they like to do is graph everything and have a lot of graphs sort of in relationship. We also see this graph-wise here at time 0. Pretty much all we have are reactants. We have pretty much no products being made. And as time goes on, obviously, we need to use up some of our reactants to start making some of our products. And obviously, we see that decrease in our reactants continue and an increase in our products basically continue as time goes on. And we can actually do a very simple sort of kinetics experiment, and we'll do a version of it today in lab. But one way that we can sort of follow the reaction in terms of its kinetics and what's happening is if we do some type of reaction that has a solution, for example, that has a color. And we could look for either one of two things. In the example that we see here, it is the Br2 that basically has this color here. And obviously, with a lot of reactants present, we do see much darker color of, say, orangey type color. And as the reaction sort of proceeds to the product side, pretty much all these guys are colorless. And we start to see, obviously, the color of the solution starting to lighten to colorless there. As we could tell by the end beaker, are pretty much have mostly products, as there's nothing that's going to give us that sort of color. In the experiment today, you're actually going to mix some things together and wait for the color actually to appear. And that's how you'll know sort of the reaction is going to be done. So because there is sort of a solution that has some type of color, we can use something as simple as like our spec 20 that we used in a previous experiment and spectrophotometry, basically to analyze what's going on. And as we know, we basically have a light source that we select a specific wavelength, and that wavelength that we select, like we did when we did the Kool-Aid experiment, and there was the spectromaster where they chose the maximum absorbance, right, to set your, say, spec 22 so that you can get absorbance values that fall on the schedule here or on the line. and not go above or outside of the range of the machine, we can very simply follow really the absorbance values of solutions. They have very nice machines now that does this for you, like they could take the concentration every second of your solution. So very commonly what you do is you would take your two solutions, kind of keep them separated, then mix them together, then slap it into the machine. And basically the machine will do it for you every second, basically take an absorbance value. You can very clearly see, for example, the concentration of, say, every reaction is decreasing with time and so forth by the increase or the decrease in absorbance value. Obviously, absorbance is related to concentration, especially if it's a solution that has a color. So the change in the concentration, for example, in this reaction of the Br2 is proportional, which is what that symbol means, to the change in the absorbance value. So in this particular reaction, if you were following sort of the absorbance value over time, you would see obviously a decrease, obviously, in the absorbance value over time as it becomes more colorless. You could also, if you wanted to do it in the opposite way, if your sort of solution that has a color is on the product side, you would see it obviously start to increase in absorbance over time if you did have, like, say, a product that was a color solution and there was no color on, say, the reactant side. Clearly, much like the Kool-Aid experiment, you can only do this if you have something that obviously has some type of color. Otherwise, there was no way you could follow the absorbance value, right? Because the darker the color of the solution, the more light's going to be absorbed. And obviously, if there is no color in any of the solution, they're all colorless, you will have no absorbance on anybody, so there would be no way to follow it. So this is a very common sort of kinetics experiment, kind of pour things together, put it in there, and over a period of time, you can very quickly sort of relate the absorbance to the concentration. We do that by using what we also use a little bit in our experiment, which is Beer's law, which one version of it is something like A is equal to BC. That is our absorbance. That's our Beer's constant. And that is our concentration. So by taking some very simple sort of calculations and measurements, you can relate your absorbance values like you would have a graph here, and you can very easily, using something like Beer's law, turn it into the concentration of your reactant over time. And you could also, very quickly sort of relate how the concentration is changing versus time. Any questions on that there? Now, when we talk about rates, a lot of times we do sort of look at what is sometimes referred to as the average rate for the reaction, as opposed to maybe what is sometimes referred to as the instantaneous rate. So I sort of think about this like, for example, if you're driving, right, which is basically a rate depending on how fast you're going, right? If you're driving 25 miles per hour, you're going 25 miles an hour, right? That's your rate. Basically, if you keep that at a constant sort of value all the way through, you pop it on cruise control or something like that. So much like when you're driving, if you're driving, say, from here to wherever, Arizona or someplace like that, maybe along the way, right? You're doing 65, 75, 80-ish, maybe in some areas 90, hopefully not too much 90 or higher, and so forth. But if you were to sort of average your overall trip from beginning to end, maybe on average you drove like 70 miles per hour on the entire trip. But there were portions in that trip, probably if you sort of zoomed in on just a specific period of time, maybe you were traveling faster, or maybe you were traveling slower than, say, 70 miles per hour. And that would be more of an instantaneous rate. So an instantaneous rate is sort of a snapshot of how fast, for example, the reaction is happening over a specific period of time. A lot of times we look at sort of the average rate over the entire reaction and sort of what's happening. And just like sort of when you're driving, there are certain points along the way, perhaps things are reacting faster and maybe they're reacting a little slower. But as a whole, when you take the average rate, you get basically an idea of overall how things are changing with time. So if we were going to calculate the average rate here of our BR2, again, we would have our negative because it's a reactant change in concentration of BR2 over the change in time. And once again, this average rate is typically, as I mentioned, a positive number. And that's because, again, here in this case, our final will actually be smaller than our initial which will be larger, once again, giving us a negative number on top, and that negative there, again, counteracting that, and obviously our time. If you wanted to sort of calculate for an instantaneous rate, you could take the slope of the tangent of the line, for example, and you could sort of calculate it, sort of that instantaneous rate for a specific period of time. As I mentioned before, in kinetics, there's a lot of sort of graphs that are oftentimes used, and there is actually a relationship that, is sort of graphical as well, that you could get, that does give you sort of a constant sort of value for what's going on. And if we were to write something which is sometimes referred to as the rate law, which again is a slightly different than the rate expression, and here we would have something like the rate is equal to K times concentration of Br2. This is our rate, typically in molarity over seconds. The lowercase k here is our rate constant. And I emphasize kind of lowercase k because if you do take 200B, capital K is the equilibrium constant, which is slightly different. So typically when you're dealing with sort of rates and kinetics, you want to make sure that the K actually is lowercase k, because that indicates the rate constant. Obviously, this is our concentration of our reactant in this particular case. If you rearrange this rate law and you actually solve for the rate constant, you will get a rearranging that looks something like this. And what we will end up with, for example, in this one is the rate is molarity over seconds, and the concentration of Br2 is molarity. So the molarities will cancel, and will actually give us reciprocal seconds as the unit here for the rate constant. And one of the important things in kinetics is understanding sort of what type of order a reaction is, for example. And a lot of times you can figure that out by looking at the units associated with the rate constant. Now, there's typically three sort of common type of orders of reactions that we'll talk a little bit about in this chapter, which is first order, second order, and zero order type reactions. And a lot of times there are specific sort of formulas that you need to use depending on whether it is a first order, second order, or zero order sort of reaction. And in a number of problems, they don't automatically tell you, for example, hey, you're dealing with a first order reaction or you're dealing with, say, a second order reaction. But what they will give you is the value of the rate constant, and you can see the units that are associated with that. And from the actual units, you can basically know, oh, this is a first order sort of reaction or a second order reaction. So in kinetics, the rate constant is really important. It is also, if you want to think about it, sort of how fast the reaction is taking place. So if you have a larger rate constant, then typically the reaction is happening a lot faster. If you have a kind of a smaller value for a rate constant, it is happening perhaps at a slower rate. But it is a constant number, and we can see that over a period of time, sort of the instantaneous rate here is changing a lot. But if we solve for this relationship of the rate constant, it essentially is a constant number all the way across at any point along the way. So the rate constant is a value a lot of times that we look to try to calculate and figure out in kinetic sort of experiments. And for example, here in this example, it is 3.5 times 10 to the minus 3, again, reciprocal seconds. That particular number is not important, but it's just related to this sort of graph or this sort of specific experiment here. Now, what happens if we do not have a reaction, for example, that we can follow the absorbance value? Maybe we do produce everything that is sort of colorless, which is really the situation in this reaction. They did just put some dye in there so you can see it in the picture. But pretty much everything here is colorless in this sort of reaction. And trying to do, again, a kinetics experiment with colorless sort of solutions, reactants, or products is pretty much useless because you're not going to get any type of absorbance values. But one thing that we do get here is the generation of a gas. And because we are generating a gas in this case, we can use something like the ideal gas law. And as we talked about a number of times in some previous chapters, if you solve for N over V, which is equal to P over RT. N is our moles and V is our liters, which is basically our molarity, which is our concentration. So in this particular case, we actually can figure out or keep track of how the concentration of O2 in this case is actually changing with time by just simply following the change in pressure. And that is because the only gas in this reaction is O2, which is on the product side, which means the only way that we would get a gas formed is we would have to make the O2 on the product side, and that would be the only way we would get pressure. So we know that we start to see an increase in pressure or pressure starting to increase. That means we are definitely making more products and we have more gas being made in this particular reaction. If you did this reaction, you most likely would have done it in a more sort of same temperature room, which means the temperature is pretty much going to stay the same. R is obviously a constant. So in this particular case, by simply just following the change in pressure over time, you can then back sort of calculate it and relate it to how the molarity, for example, or the concentration of O2 is changing with time. So you obviously can do kinetics even if you don't have solutions or reactants or products that have some type of color and do some type of absorbance value. Again, this is another sort of approach that works really well, especially obviously if you're producing a gas. You also could do it the opposite. Obviously, if you are starting with gases and the pressure and you form something on the product side that have no gases, then you would be looking at sort of the opposite effect. The pressure would start high and obviously end low as you're decreasing the amount of gas molecules in that case. So when we talk about these rate expressions, of course, everything that we talked about a lot in this semester deals with stoichiometry, and kinetics is no different. So when you're dealing with reactions and kinetics, you do have to take into account stoichiometry and really the mole-to-mole relationship that occurs. So obviously, as we know from this equation, if we were looking sort of at our mole-to-mole relationship, we see that for every 2 moles of A, we get 1 mole B that is produced in this particular case. And you do need to take that into account in terms of the stoichiometry of this reaction and the kinetics to get sort of the correct, obviously, answer based on that mole-to-mole relationship. So when we would write our rate expressions for this reaction, we would take our rate is equal to negative because again, A is a reactant. We actually will take 1 over the coefficient. So that is where the 2 comes from. It is the coefficient. And we basically take 1 over the coefficient times the change in concentration of A over the change of time. We go to our product side, which is B. Again, we do not need the negative like we were talking about earlier because it should be increasing with time. And it basically is not written here, but obviously the coefficient here is 1, which means 1 over 1 is 1. And that is basically what technically would be there, 1 over 1, but obviously that equals 1, so you don't have to worry about it. The change in the concentration of B over time. So this gives us a relationship that we could write some rate expressions for reactants and products, and we could actually set them all together. So the average rate here, which again should be a positive number, is equal to minus 1 over the coefficient of A times the change in concentration of A over the change of time. That would equal minus 1 over B, the change in concentration of B over change of time. That equals now on our product side positive 1 over the coefficient of C times the change in concentration of C over time. And lastly here as well, 1 over the concentration of D over the change in time. What this allows you to do is essentially for any reaction, all you really need to know is how one reactant, one product is changing with time, and you pretty much can figure out how everybody else in that reaction is changing with time by using these relationships. You also, if you just know the average rate as well, you can figure out how everybody else is changing. These are all set up equal to each other. which means you don't necessarily have to use the entire reaction if you, for example, just had information about A and D. You could just pull those out separately and go the rate is equal to -1 over A, change in concentration of A over the change in time. You also write a rate expression for just D by itself, 1 over D, change in concentration of D over the change in time. So how would this be helpful? For example, if you knew how A was changing with time, that would allow you to figure out the average rate for that reaction. The importance of that is that average rate for that reaction is the same average rate for that guy, which then would allow you to figure out, for example, how D would be changing with time. So just knowing one piece of information in sort of this relationship of a reaction in terms of its kinetics will allow you basically to figure out how anybody else in that reaction is basically changing with time. Any questions on that? As I mentioned before, this average rate is typically a positive number. But for example, if you were solving for how specifically the concentration of A was changing with time, you would end up, for example, with a negative number because it should be decreasing with time. Same thing if you were specifically calculating for just how the concentration of B over time is changing. Because it's a reactant, you will end up with a negative number. If you're doing C over time or D over time, you will end up with positive numbers for those. So it is possible to end up with sort of a negative value for a reactant in terms of how that concentration is changing with time. But if you're calculating the average rate of the overall reaction, taking everybody into account, that should end up always as a positive number. Questions on that? So why don't you take a second here and just write the rate expression for this reaction and see what you come up with. Okay, so let's take a look. So again, we're going to start with our rate is equal to, we're going to start with our first reactant here. Because it's a reactant, we want negative, and we do want to go 1 over the coefficient, which is really 1 over 1, so you don't really need to put that. That would be the change in the concentration of CH4 over the change in time. That would equal our next reactant, which should also be negative because it's a reactant decreasing with time. Here we do want to go 1 over the coefficient, which is 2, times the change in the concentration of O2 over the change in time. That will equal now to our product side, which should be positive. Once again, here we do have a coefficient of 1, so we don't really need to put that in there. So that'll be the change in the concentration of CO2 over the change in time. And lastly, here we have a coefficient of 2 for our H2O. And again, it's a react product, so it should be increasing with time. So 1 over the coefficient, change in the concentration of H2O over the change in time. So once again, they're all equal to each other. Like I said, you kind of pick and choose the ones that you maybe have information about, and you can write separate rate expressions. Now, this is a really good way of sort of comboing the sort of stoichiometry part of the calculation with the kinetics part of calculation by taking 1 over the coefficient. Kind of does all the sort of stoichiometry for you at the same time. You can, in a lot of cases, and in certain cases, if you wanted to, just kind of do a stoichiometry problem, a multiple relationship, and then kind of do the kinetics part separately. So you can sort of do it separately, but if you take 1 over the coefficient, it kind of combos all the calculations sort of together, and you don't have to necessarily do like kind of 2 separate things. Like here's a stoichiometry part, now I got to do the kinetics part kind of together or separate from each other. Any questions on that there? So let's take a look at one here where we actually do have some numbers and sort of see how we could use it with numbers. So for this reaction, given the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds, we want to calculate the average rate in the first 10 seconds and also how the concentration of H plus is changing over time. So really in this sort of problem here, we're given information about I minus, and we ultimately are interested in H plus. And what I would do personally is just write 2 rate expressions for each of those things. and really just ignore the rest of the reaction because we're not really dealing with anybody else in that reaction. So just writing our normal sort of rate expressions, we could write that the rate is equal to, and again, I minus is a reactant, so it should be negative, 1 over the coefficient, which is 1 over 3. Once again, that's going to take into account the stoichiometry, the change in the concentration of I minus over the change in time. We could also write a rate expression for our H plus, which is the rate is equal to, once again, H plus is also a reactant, which means it will be negative 1 over 2, which is the coefficient, the change in the concentration of H plus over the change in time. So these are our two sort of rate expressions that we want to use in this particular reaction. Now, when we look at the information sort of given to us, we are given that the concentration of I minus initially was 1 molar. The concentration of I minus finally was 0.868 molar. And this is really over 10 seconds, which means kind of initial time 0 seconds probably consume, and final time kind of 10 seconds. So all that is pretty much this part of it here. Is the change in the concentration of I minus over time. So I'm going to use that sort of rate expression to help me calculate it there. So the rate's going to equal minus 1 over 3. Once again here, when we do the change in the concentration of I minus, it is final minus initial. So that will be 0.868 minus 1 molar divided by basically final minus initial, 10 minus 0 seconds. This is important because once again, that's going to give us a negative number, which is going to go with this negative here to again give us a positive value for the rate. And in that case, that's going to be 0.868 minus 1 divided by 10 and divided by 3. And that will give us a rate of 0.0044. The units here actually don't cancel, so that's molarity over seconds, which is a rate unit that we typically see. So on average, this reaction is changing basically 0.0044 molarity per second. Any questions on that there? Now, we are also interested in specifically here the reactant of H plus, how it is changing. What we just calculated is the rate of the overall reaction, which is also the rate here specifically for our H plus as well. It is the same number. So everywhere the rate's basically the same. That allows us to basically put that into our equation there, 0.0044 molar seconds is equal to minus 1 over 2, the change in the concentration of H plus over the change in time. So in this particular case, we are actually looking to solve for this guy right here. So what we need to do actually is multiply the 2 to the other side. But it's not just the 2, we also need to multiply or take the negative to the other side as well. So we really need to kind of multiply negative 2 to the other side, and both sides basically, and that will cancel there. And that will get us that our specifically here, our H plus concentration, I'll go up here, our H plus concentration over time is going to be negative 0.0088 molar seconds. As you can see here, and as I talked about a second ago, we do end up with an actual negative value here for how that reactant is changing with time. And that's okay because it should be decreasing with time. And that is why we end up with a negative 0.0088 molar seconds by multiplying that 2 over. And again, that 2 is important because of the stoichiometry here. It is basically has a coefficient of 2, which means on average, that specific reactant is changing twice as fast as everybody else in the reaction, basically, or the average sort of rate of that reaction. And that's because of the stoichiometry that's there. Basically, you got twice as much of it there. So it's available to react a lot quicker, and we will see a sort of greater decrease in the amount of that reactant. Question on that there. So why don't you try one here? If 2.4 times 10 to the 2 grams of NOBr has a molar mass of 109.91 grams per mole, decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes, what is the average rate of Br2 production in molar seconds? So again, here we have information about that guy, but we want to end up there. So see what you come up with. So let's take a look. So once again, really best thing to do is just focus on kind of the two things that are obviously involved here. We could write a rate expression for each of these. So the rate is equal to minus, again, because the NOBr is a reactant, 1 over the coefficient. That, again, will sort of combo the stoichiometry part of the calculation together. The change in the concentration of NOBr over the change in time. We also could write one here for our Br2, which would be the rate is equal to, because Br2 is a product, it will be positive. Also, the coefficient here is 1, so you really don't need to put it in there because it's 1 over 1. So basically, we will have the change in the concentration of Br2 over the change in time. Any questions on those two? Now, since in this case we really have information about NOBr, that is going to allow us really to sort of calculate this part of the rate expression from the information given to us. Obviously, the top part is the change in the concentration of NOBr, which means we really need to calculate the molarity here of our NOBr, which would be obviously our moles per liter. This is going to be our liters part here. That is basically 200 milliliters, which is the same as 0.2 liters, basically, if you convert it into liters. The moles part is going to come from just a basic grams to moles calculation from the periodic table. So we could take 2.4 times 10 to the 2 grams of NOBr. We'll use the molar mass that was given to us. If not, obviously, you would go to the periodic table to get that. And that is going to get us here 2.4 to the 2 divided by 109.91. And that is going to be 0. Well, it's not going to be 0. It's going to be 2.1836 moles. And obviously here we then could put that obviously as the top part there, 2.1836 moles. And if we divide that obviously by our 0.2 liters, that will get us 10.92 molar of our NOBr. That is essentially the top part here. I do want eventually my rate there to be in seconds. So my time aspect is in minutes. So I'm just going to upfront do a conversion here to get it into seconds. So everything's sort of in the right units. So minutes is 60 seconds, I hope. That's 300 seconds. So now I have really my molarity, which is the top part. I just got my bottom part, which is the time. So I do have what I need for the box. So this is going to allow me to figure out how the NOBr is changing. The rate's going to equal to minus 1 over 2, negative 10.92 molar divided by 300 seconds. The reason I put a negative is this, again, is a reactant, which means it's decreasing with time. Although we do have the number that goes up there on top, it would be found by taking final minus initial, which should give us a negative number, along with this negative, which once again will turn our rate into a positive number. So again, if you don't put the negative there, you're going to end up with a negative value for the average rate, which you shouldn't have. So you can get rid of it if you want, but that's basically why we would want to put the negative here. When we do that, that will give us a average rate there of 0.01, we'll call it 82 molar seconds. Right. We then want to figure out how is our BR2 changing with time. And we have our rate expression right here for that. And that is the rate is equal to the change in the concentration of BR2 over the change in time. And frankly, this number we just calculated is the rate. So that is basically what that equals. It is basically the same number. It will equal 0.0182 molar seconds will actually be the rate there of how BR2 is changing with time. So BR2 is actually increasing at the average rate of the overall reaction that's happening in this particular case. Any questions on that there? So this is the way, as I mentioned before, that you can sort of take the stoichiometry and the kinetics part all together. If you wanted to, as I mentioned before, do just a stoichiometry calculation, you could do that as well. And what that would look like is you would kind of do the same step up to here. You would get your 2.1836 moles of NOBR. You would just do a regular mole to mole relationship from the equation, which is a 2 to 1. 1 mole of Br2 is 2 moles of NOBR. That will get you 2.1836 divided by 2, get you something like 1.0916 moles of Br2. Now that you did the stoichiometry part, you could just do all the kinetics part of it, which is I need to turn that into molarity. So I'm going to divide it by 0.2 liters. So you'll divide that by 0.2 liters. Will give you something like 5.459 molar. You then would divide it by the time aspect of it, which is 300 seconds. And if you divide it by 300 seconds, you end up with obviously the same number we just ended up with there, which is that number. So here again, like I said, you can kind of do the stoichiometry part first if you wanted to, and then just sort of incorporate in all the kinetics aspect of it at the end, and it will come out the same. The other way, again, just sort of does it all together in the same calculation without that. That's basically why we take, by the way, 1 over the coefficient, as you can see here. That's basically where that comes from, is the mole-to-mole relationship gives you that 1 over the coefficient in that particular case. Any questions on rate expressions or how to calculate those there? All right. Now, in terms of rate, there's a lot of things that can affect the rate of a reaction. The nature of the reactants, what kind of reactants are sort of reacting, their sort of physical state. Small molecules tend to react faster than larger ones. Gases tend to react faster than liquids, and liquids react faster than solids. And that's just think about the energy aspect of it. Obviously, gases are flying around with a lot of energy, which means they're more apt to come in contact with each other and start reacting. Liquids still have a little bit more energy, obviously, than solids. So that's going to allow it to react a lot easier. Solids are pretty much your lowest in energy, so they're just kind of sitting there. So they're not going to react as much or as fast, probably, than a liquid or a gas. But there are certain solids that react faster than others. Powdered solids react faster typically than block solids. And that's more surface area for the reactants to happen. Maybe some of you experienced that with like the magnesium, for example. As I mentioned before, when you're coiling that magnesium, that last experiment we did, if you coil it really, really tight, it doesn't allow a lot of surface area, obviously, for that solid to react with the HCl, and it's going to react a lot slower than if you coiled it in a sense where a lot more of the magnesium, for example, was available to the HCl. It would probably react a lot faster. When we talk about there are certain metals that are, for example, more reactive than others. That activity series of metals that we talked about, that is essentially where you have all the elements, hydrogen sort of in the middle, bunch of other elements. Remember, anybody sort of higher on the activity series will react with somebody lower. Anybody lower on the activity series will not react with anybody higher. We saw that with really single replacement reactions where somebody was coming in and trying to kick out another element. Ions also react a lot faster than molecules because, frankly, where you find ions pretty much is in solutions, and they are floating around, which means they're good to go. They're ready to react. You know, nothing else has to happen. for them to be good to go. They are by nature just good to go. Temperature is an overwhelming type of factor in terms of reaction rates and how fast, for example, or how slow, for example, a reaction may take place. Increasing the temperature typically will increase the reaction rate. It gives everybody a lot more energy. And there's really kind of two major things that are needed for a reaction to take place. Things need to hit each other, and they need to hit each other with the right amount of energy. So at a higher temperature, you're going to have a greater proportion of molecules, for example, with sufficient amount of energy for that reaction basically to take place. There's an actual relationship and equation that relates temperature to the rate constant that we'll see a little bit later on in this chapter here. Catalyst is another thing that can affect the rate of a reaction. I think we talked a little bit about catalyst along the way here, but again, a reminder that a catalyst is not a reactant. It is not a product, and it does not get used up in the reaction. It is there simply to facilitate, in most cases, the reaction happening a lot faster. There are some catalysts that actually slow down the reaction. Those are sometimes referred to as negative catalysts, but I would say 99.9 times of the time, probably if somebody is talking about a catalyst, they're referring to it in the sense of it being something that will speed up a chemical reaction. Catalysts are kind of like mixtures as well. They can be homogeneous catalysts, which means that the catalyst and what is reacting are all in the same phase. So a very common sort of catalyst that's used are acids as catalysts, and acids can react really well as a solution with other solutions to help facilitate the reaction occurring. Heterogeneous catalysts are ones that are in different phases. So a lot of catalysts are metals, for example, and things that are reacting, say, are gases. And a lot of times you will find the catalyst written on top of the arrow. So maybe you'll see something like platinum written, maybe H plus, which is an acid catalyst. And a lot of times the catalysts are listed usually on top of the arrow to indicate that they are there to sort of facilitate the reaction happening faster, but not really a reactant or product, which is why they're usually placed on top of the arrow. Also, concentration is a really good factor as well. Typically, if we have a larger concentration, there is a greater frequency of molecules able to react. And when we think about molarity, for example, the true definition is moles of solute over liters of solution. And when we talk about molarity, which is a solution, basically, there is the solute and the solvent that make up that solution. And out of those two, it is always the solute that's really the thing that's reacting. And that's because that's also the name of the solution. So if you have a 6 molar hydrochloric acid solution, hydrochloric acid is the solute, and that's really what's reacting. The water part of it, which is the solvent, is not really doing anything. It's really that sort of concentration of the solute. And that means that if you have a larger concentration, you will have a lot more solute present in the solution. More solute present means greater chance of everybody coming together a lot quicker and faster and more efficiently. And that will also result usually in a faster rate. Gases also depend on the partial pressures. As we know, higher pressure typically means you have a higher concentration of gases. And that also would allow you to have things reacting a lot faster. In addition, at a higher pressure, you usually have a smaller volume, which means everybody will be near each other, a lot closer to each other. This is going to encourage sort of collisions and reactions to occur. So let's talk a little bit about the rate law and the relationship of what it looks like and how we sort of calculate it. The rate law, as I mentioned, is a relationship that's used a lot in kinetics. And one of the couple of things that we see in the rate law, which is one for like this. This is the rate law for the expression or the reaction above it. The rate is equal to K times the concentration of A to the X and B to the Y. Once again, that is our rate, which is our molarity over seconds. That is our rate constant. These are our concentrations of our reactants. And X and Y, in this case, are what are referred to as the orders. and X in this case is the order with respect to A, and Y is the order with respect to B. And one of the important things that you see with the rate law is it's all about reactants only. So unlike the rate expression where we sort of relate everybody in the reaction, the rate law only deals with reactants. X and Y are the orders, and it is always found experimentally. So usually the rate law is always found experimentally, which means typically you will get like tables and you'll have to do some calculations to figure out what X and Y is. X and Y is not, in the case of the rate law, it is not the coefficients in the balance equation. So we do not use the coefficients as the exponents here. You actually have to look at the experimental data to sort of calculate those things. So what is X and Y in the orders? You could think of it as kind of like the proportion of X and Y that's necessary to be mixed together to produce a reaction at a specific rate. And why would it be important, for example, to know, what the orders are and what the rate law is for a particular reaction? So let's just say, hypothetically speaking, we calculated the rate law for this guy, and we found that the order for X and Y was 1 each. So the rate law would be, in this case, if it was 1 and 1 for each of those, would be the rate's equal to K times concentration of A times concentration of B. By the way, the overall order of the reaction can be found by adding those individual ones together. So in this particular case, most of the time we don't write ones, but these are going to be ones here. So the overall order in this case is going to be 1 plus 1 is second order. So this would be a second order overall reaction by adding those together. And that also is important for, again, for selection of correct sort of equations and relationships as well. So why is this important? Let's just say we did this reaction and we started with a concentration of A of 2 molar and a concentration of B of 2 molar in this particular case. So we did, say, our first reaction at those two concentrations. If we were to sort of stick it into this equation, that would give us basically the rate is equal to basically 2 times 2, and that would give us like 4 molar seconds, for example. I'm not going to worry about the K because it's a constant, so it'll be the same as long as the temperature and all that stays the same. It's going to be a constant value, but that will be really the same sort of value. Now, let's just say that you did this reaction and you found it to be way too fast, for example, for you to take measurements. And this happens sometimes when you are doing an experiment and you mix things together. And if you're like taking all day to get it into the machine, the reaction in some cases can be over before you actually get into the machine to take your measurements. There are reactions that are like super fast. They kick off really fast. And by the time you get there, you're actually catching like the end of the sort of reaction, not the entire sort of reaction. So you go, well, that's not good. I want to slow it up, maybe. I want to slow this reaction up. So let's just say, okay, in this case, I want to run A at 2 molar, but I'm going to cut the concentration of B in half to 1 molar. And if I put this into my rate law here, that would give me, again, the rate is equal to, in this case, basically 2 times 1. And that would now take us down to an average rate of 2 molar seconds. I cut the concentration of B in half here. The resulting rate also got cut in half, right? By doing that. So this is a way I could slow it down, right? If I wanted to speed it up, maybe I would, concentration of A is 2 molar. Maybe I bump up B to 4 molar. Now when I put it in here, I have K 2 times 4 gives me 8 molar seconds. I increased, right, the concentration of B in this case, doubled it, and that actually doubled the rate. So maybe the reaction was too slow for what you wanted it. You wanted to speed it up. You can play with the concentrations, and it would have an effect on the rate. Now, in this case, would it matter which one I did that to? In this case, it wouldn't. Although I changed B in this case, I could have just changed A, and it would have resulted in the same sort of relationship because the orders of both of those guys are basically 1 each. Now, let's say we did an experiment and we found that the rate law for this reaction was K, A to the first order and B to the second order. And in this reaction, the overall reaction would be 1 plus 2, which would be a third order reaction by adding those sort of exponents together. Now, let's just say we started with the exact same concentration that we did here in number 1. And in this case, that would give us that the rate is equal to K times 2 and 2 squared. So that is 4 times 2. That's basically giving me 8 molar seconds. In this particular case, because the order of B, it's actually second order, even though we started with the same concentration as the one on the right, for each of those guys, we actually have twice the starting initial rate, right? So this reaction out of the gate is going to be twice as fast as the previous reaction that we did on the right-hand side. We will also see a greater change in what happens if we did the same thing there, where we cut the concentration of B in half. So if we did that the same way and we cut it in half, we would have 2 times 1 squared. That's going to give me 2 molar seconds. In this case, I cut the concentration in half of B. My rate actually went down by a factor there of 4, right? So it went from 8 to 2. So it slowed down significantly, right? In this particular case. Now, in this case, though, if I did the concentration of A and cut that in half and left my other guy initially at 2, we would actually get 4 molar seconds. So in this case, there is a difference if you did A versus B, right? If I only cut A in half, my rate only dropped half, right? It only went down to 4 versus all the way down to 2 in this case. So by knowing these orders, knowing the rate law, if you needed to in a real life situation, sort of figure out, I need to kind of speed up this reaction, I need to slow down this reaction. There are certain reactants that will have, obviously, in some cases, a greater effect on the overall rate by playing with their concentrations than others. Now, what happens if I did a rate law where I ended up with A to the 1 and B to the 0? When you take something to the 0 power, what does it equal? It equals 1, right? Which basically means that equals 1. Which means in this particular reaction, if I change the concentration of B, will it have any effect on the rate? It will not, because it will always just end up being the same 1 no matter what number you throw in there. You can increase it like tenfold, it will still end up being 1, right? Because it's to the 0 order. The only thing that would affect this reaction is actually A. So if you had a rate law for a reaction that you were working with like that, and you wanted to affect the rate, either make it faster or slower, your only option in that case would be you have to do something to A to kind of speed it up or slow it down, because you can do whatever you want to be, it will not affect it. Any questions on that there? So how do we calculate? As I mentioned, rate laws are typically calculated from experimental information. So typically you will be given a table such as this. And typically in this table, there are the concentrations of your reactants. There's also the initial rates. And there's usually a number of different experiments that were performed. So you could do it one of two ways. You can either look at the relationships in the table and figure out how things are changing, how the concentration is changing, their rates are changing to each other. But most people have a difficult time sort of doing that. So I find mathematical approach is probably the better approach for it. So you can use this relationship that the rate of 2 is equal to K A to the X, B to the Y, divided by rate 1 is K A to the X and B to the Y. So the rate 2 and rate 1 here doesn't mean you just go to the table, take the first and second entry. It means that you go to this table, and in this particular table here, there's only 3 entries. You could have ones that have 4, 5, 6, a ton of entries in the table. But what you are looking for is, in this particular case, 2 entries where one of the reactants concentration stays constant and the other one varies. And if you have 3 reactants, you would want one where 2 of the concentrations stay the same and 1 varies. The idea here is to have only one variable, which makes mathematically easier to solve, right? We have multiple variables, not so good. So if we wanted to do that, for example, if we look at this reaction, our generic rate law would be the rate is equal to K times F2 to the X and ClO2 to the Y. So our goal from this table is to try to figure out what each of those values basically represent. So to do that, I'm going to go to the table, and I can see that in experiment 1 and 2, the concentration of F2 stays the same. So I'm going to start with that. I'm going to look at experiment 1 and 2. And when I look at experiment 1 and 2, just to give you prettier numbers usually when you do this calculation, you typically want to take the one where the rate value is the larger number and put that on top. So if you take the one that has the larger rate and put all that information up on top, that will usually give you a lot more whole numbers than decimal numbers. So a lot of times that's easier for people to kind of see what the end result is going to be. So what I'm going to do is, because number 2 is the larger rate, I'm going to put all of that up here, up on top. So all of that information for experiment 2 will go up here. That means we have 4.8 times 10 to the minus 3 is equal to K times our concentration of A, which is 0.1 molar to the X, and for our B, 0.04 molar to the Y. So everything that I put up on top is all the information for experiment 2. So basically, you don't want to mix and match here. So all the way across here is everything that went up there. Now I'm going to put everything for experiment 1 here on the bottom. And to do that there, that's going to give me 1.2 times 10 to the minus 3 molar seconds. K, our 0.1 molar squared, and our 0.01 there, molar to the Y in this particular case. And what we're going to do now is just some math. So if I take 4.8 times 10 to the minus 3 and divide it by 1.2 times 10 to the minus 3, that is going to give me a 4. When I come to this side, that is the rate constant, and that is a rate constant. And the name is rate constant, which means it's the same number. Although I don't know what it is at this point, it should cancel out because it's the same number. When I come to my concentrations that are the same, these x's are also going to be the same number. I don't know what it is at this point, but I do know that they should cancel out. Now, when I come over here, that's basically 0.04 divided by 0.01 gives me 4 to the y in this case, basically. Any questions on that there? You could probably clearly see that y in this case is going to equal 1. By the way, if you didn't have a pretty number, you take the natural log of 4, or the natural log of 4 brings the y down, divide the natural log of 4 to both sides is one way to get rid of it, and you will end up with 1. So if you don't have really pretty numbers, take the natural log of both sides and divide it out. That will get you there. So what that tells us is the order with respect to ClO2 is going to be 1. Now that we did that, we want to go back to our table, and we want to find 2 entries where the ClO2 is going to remain constant and the other one will vary. And in that case, it looks like experiments 1 and 3 will do that. That will keep those guys constant. So experiment 1 and 3. We're going to do the same thing. I'm going to go with this guy up on top because that's the larger rate. That will give me 2.4 times 10 to the minus 3 molar seconds equals K, 0.2 to the X, 0.01 to the Y. We're going to put everything from experiment 1 on the bottom, 1.2 times 10 to the minus 3 molar seconds. K, 0.1 molar to the X, 0.01 molar to the Y. Once again, we're going to do some math here. That's going to give us a 2. These K's should cancel. When we do the next guy, that's going to give us a 2 to the X, and these guys should also cancel. And here we can see that x is equal to 1 in this case as well. Any questions on that? What we just did is use the experimental information to figure out the orders. That means that the rate law for this reaction would be K is equal to F2 times ClO2. The overall order in this case for this reaction will be 1 plus 1, which is a second order reaction. Any questions up to that point? Once we found the actual completed rate law and actually have the orders for everybody, we then can use the completed rate law to actually calculate the value of the rate constant. So in this case, I'm going to solve for the rate constant, and that would be K is equal to the rate divided by the concentration of F2 and ClO2. Basically, I'm taking these guys and dividing it to the other side, along with his proper orders. Obviously, in this case, both of the orders are 1, but if there was like a 2, we would need to keep the square with it and all that. Where do we find this information? You could then go back to your table and you could actually choose any entry you like. You could choose number 1, you could choose number 2, you could choose number 3. Just can't mix and match. You got to choose one and use them all. So for me, I'm going to use the first entry, which means the first rate there is 1.2 times 10 to the minus 3 molar seconds, divided by the concentration of my first reactant and the concentration of my second reactant. That is going to give me a rate constant in this case of 1.2 to the minus 3 divided by 0.1 and divided by 0.01. Going to give me 1.2 units. Molarity on top will cancel. Molarity on the bottom will cancel. Still leaves us 1 over molar seconds, which, by the way, are the typical units that you find for a second order reaction for the rate constant. So this is a very common sort of problem that you need to know how to do. You can take the table. You want to find 2 entries where one stays the same and one varies. And you could use that to figure out the orders. Once you figure out the orders, then you could go and figure out the rate constant. Once again, if I put the values in for experiment 2 or experiment 3 here, I will end up with the same rate constant. It should end up with the same value no matter which one that you choose. Any question on any of those there? So as we see there, they are always determined experimentally, our rate laws. It's always in terms of the reactants, no products. And once again, in the rate law, the coefficients are not where we get the orders from. You do have to sort of use the experimental information to find it. All right, so why don't we try one here, see what you come up with. Determine the rate law for this one with the orders. And what is the overall order? And what is the value of the rate constant? So take a few moments, see what you come up with using this information. Okay, let's take a look and get into the end here. Once again, we can start with kind of the generic rate law, which will be the rate in this case is equal to K. Remember, it is only our reactants involved. So our first reactant, we could call it to the X. And our second reactant, we could call for the Y. Remember, we're going to use this table basically to figure out those orders. And when we do so, we want to look for 2 entries where one stays the same and one varies. And again, in this case here, since we only have 2 reactants, that's what we're looking for. Again, if you had multiple reactants, you want to just only have one variable. So experiments 1 and 2 keeps that first guy constant there. So putting in our values, I'm going to choose experiment 1 here because it has the larger rate to put up on top. So again, I'm just going to put everything from experiment 1 up on top. And again, we're just going to kind of fill in our normal sort of thing here. For experiment 2, we're going to put everything on the bottom there. X 0.017 to the Y. Once again, we're just going to do the math. So that should give us a 2. Once again, the rate constant on top and bottom should be the same number, although we don't know what it is at this point. The order here for both these x's should be the same, although we don't know what it is at this point. That should cancel all that out. And once again here, we will have our guy there, which should give us a 2 to the y. And once again here, our y will equal 1. Any questions on where any of those numbers came from? Now that we did it for the first reactant and kept constant, we want to go back to our table and find two entries where we keep the other guy constant. And in this case, it does look like experiment 2 and 3 will do that for us in this case. We'll keep those two guys constant. So we'll look at experiment 2 and 3. Once again, I'm going to choose the one with the larger rate and put it up on top. So that's going to be experiment 3 for me. 4.4 times 10 to the minus 4 molar seconds equals our K, 0.16 molar to the X, 0.017 to the Y. I'm going to then put everything from experiment 2 on the bottom, 1.1 times 10 to the minus 4 molar seconds, K, 0.08 to the X, and 0.017 to the Y, which we're keeping constant. Here doing our math, we're going to get a 4 is equal to, again, our K's will cancel. That's going to give us a 2 to the X. And again, this guy is going to cancel. In this case, you could also probably easily see that X in this case is actually going to equal 2, our second order with respect to that guy. Any questions on that? Now that we have that, we could actually write our completed rate law, which is the rate is equal to K times our S2082 minus, that was to the second order, X, and our I minus to our first order. That would be our completed rate law with the orders. The overall rate of this reaction would be just adding those orders together. So 2 plus 1 would give us a third order reaction in this particular case. Any questions on that? Now we can solve for K because we have the orders. So, excuse me, K in this case, rearranging this, we're going to take all these guys to the other side, is going to give us the rate is divided by S2082 minus, once again, we do need to square it, times our I minus. And again, at this point, we could choose any entry in the table to find this. I'm just going to choose entry number 1, and that will give me 2.2 times 10 to the minus 4 molar seconds divided by 0.08 molar squared and 0.034 molar. And when it's all said and done there, we will end up with 2.2 to the minus 4 divided by 0.08 squared and divided by 0.034. Looks like 1.01. Unit-wise, molarity up on top will cancel one of the molarities on the bottom, but we will still have 1 over molar squared seconds, which, by the way, if you count up the letters, is 3 letters, and it's a third order reaction, right? Just like we counted the one last time, 1 over molar seconds is 2 letters, which is a second order reaction. 1 over reciprocal seconds, or 1 over seconds, our reciprocal seconds, 1 unit, first order. So a lot of times the number of letters you have will equal the overall order of the reaction as well. Any questions on any of those steps there? All right, we lay it up there